Welcome to rankstudent.com, the site preferred by millions of students around the globe for digital education in science and technology. I'm Dr. Ahmed. I will be your host for this chapter on mechanical properties of solids. This chapter deals with the elastic plastic behavior of solid materials. The concepts introduced in this chapter are of basic importance in civil, mechanical, aerospace engineering, as well as architecture. Some definitions: a body that regains its original shape and size once the applied force is removed is called elastic. A body that does not regain its original size and shape once the applied force is removed is called plastic. Stress is defined as the force per unit area. Stress sigma equals F over A, and it is expressed in newtons per square meters. If a force causes a body to stretch, it induces tensile stress. If a force causes a body to compress, it induces compressive stress. A shear stress tau is caused by two equal and opposite forces and two parallel faces of a body. As illustrated in the diagram on the right-hand side, a cylinder is subject to two forces, top face, bottom face. Force F, the cylinder distorts through delta X, and that is a measure of the shear stress. Another example from life itself: if you are riding an airplane, sometimes due to wind shear, as the airplane is landing, you may encounter some turbulence. What may have happened is that, let's say at 5,000 feet, the air velocity is 10 miles per hour in one direction. As the airplane descends, say 1,000 feet, the air velocity may change direction. It may be 10 miles per hour in the opposite direction. The wind shear so caused makes the plane drop rather rapidly and may induce turbulence. Strain is the unit deformation of a body under stress. Tensile and compressive strain is measured as epsilon equals delta L over L. In the diagram on the right-hand side, you have a cylinder of length L stretched by an amount delta L, so epsilon becomes delta L over L. Shear strain is measured by the distortion angle theta. Illustrated in the diagram on the right-hand side, the distortion delta X divided by the length L is the shear strain gamma, which is the tangent of theta. Usually theta is very small, and therefore tangent of theta can be replaced by theta. Similarly, volume strain is measured by volume compression. Delta equals delta V over V. Hooke's law, which is very important and is the fundamental equation for elastic bodies and forms the foundation of structural analysis. It states that stress is proportional to strain. Sigma equals K epsilon. Sigma is equal to K epsilon. A typical stress-strain curve is shown in the figure on the right-hand side. In the region OA, the material is linear elastic and it follows Hooke's law. A is the proportional limit beyond which the material does not follow Hooke's law. B is the yield point beyond which the material becomes plastic. In the region AB, the material does not follow Hooke's law, but still returns to its original shape. D is the ultimate strength of the material. E is the fracture point. At a point C, in the plastic region, the material has a permanent deformation or a permanent set, as illustrated in the diagram. The ratio of stress to strain is called the modulus of elasticity. Young's modulus y is given by the slope of the stress-strain curve. Y equals sigma or epsilon. Illustrated in the diagram on the right hand side, once again you have this stress-strain curve, which is linear, exhibits elastic behavior if it had a permanent set, which is not the case in here. It would be measured along the x-axis. The Young's modulus is determined empirically by experiment. The shear modulus G is defined as the ratio of the shear stress to shear strain. G equals tau over theta. The bulk modulus is the pressure P divided by the ratio of change in volume and the volume itself. B equals minus P divided by delta V over V, namely the pressure P with a negative sign because it's compression, the change per unit volume delta V over V. The inverse of the bulk modulus is called compressibility, designated by H. H equals 1 over B. As an illustration, a beam of length L and cross-section B by D, which is supported at the ends and is subjected to a load W at the center, deflects by delta equals WL cubed by 4BD cubed Y. This we can derive later. The important thing to notice here is that the deflection is inversely proportional to the cube of the depth of the beam. So if we wish to reduce deflection and the corresponding stress, we wish to increase the depth. But then as the depth goes down, the weight goes up, and therefore we use different sections. So for instance, an I-beam illustrated in the diagram on the right hand side, channels, and other shapes that you may have seen in construction. As another example, a mountain of height h exerts a shear force at its base equal to rho hg, where rho is the density of the rock. If we know the elastic limit of the rock, we can calculate the maximum possible height of a mountain from the equation rho hg equals the elastic limit. That's how we can calculate why Mount Everest is about 29,000 feet or so. I recommend that you log on to www.rankstudent.com, download the examples onto your mobile phone or a computer, and practice with the thousands of questions, answers, and answer elaborations we have offered. Practice helps solidify the concepts. We learn by listening, seeing, and doing. So practice, learn until you begin to recognize the patterns in physical phenomena and develop critical thinking. Thank you for your attention.